In this capsule, we'll first summarize what we talked about in some of the more recent capsules, and then the focus of this particular capsule is shown in 1D. We'll focus on this one. So in the previous capsules, we were looking at stability as a major focus in organic chemistry. So we started with stability of anions. So different types of anions, and in different cases we invoke different explanations. So here are three things that we talked about already. So electronegativity as a factor in stabilizing certain anions, and that is discussed in the capsule titled Electronegativity 2. Then in Electronegativity 3 capsule, we looked at negative inductive effects and how those are invoked in explaining the stability of certain other anions. In the latest one, factors influencing stability, we discussed how resonance explains the stability of some other ions. So we need to pick the right tool out of our bag to explain different things. Now in this one, we focus on the size of the anion. So with that, let's go into the current discussion. How does size stabilize the anions? So now we talked about electronegativity quite a bit. So when we know that electronegativity increases across the periodic table. So if you are going from left to right, most often we are looking at these atoms, and there's hydrogen and metals, and there's boron, other atoms too, but we are more often focused on these atoms. So electronegativity increases that way, and electronegativity decreases this way, and increases this way, that way increase. So as you see, fluorine is the most electronegative atom. So when we are comparing anions of this type, CH3 minus, NH2 minus, OH minus, F minus, so all this, the negative charge is on the second row elements: carbon, nitrogen, oxygen, fluorine. All of them are in the same row. When we are comparing anions in that fashion, we look at the electronegativity and say fluorine is the most electronegative atom. So fluoride ion is most stable because fluorine is able to accommodate that extra electron. So fluoride is more stable. In the order of stability, CH3 minus is less stable than amide. So this is what we discussed in one of the previous capsules, Electronegativity 2 title. Now in this one, today's discussion, we will focus on this way. What happens if you are comparing the stability of fluoride, F minus, chloride, Cl minus, bromide, Br minus, iodide, I minus. So when we do that, something interesting comes up. Okay, so when we do that, we cannot invoke electronegativity anymore. So since fluorine is most electronegative, it makes sense to think fluoride is again most stable of these following ions: F minus, Cl minus, Br minus, I minus. So it may seem at first glance that fluoride is more stable because it's the most electronegative atom. else is happening here. So what is that something else? So as you see, this is in the second row, chlorine is in the third row or third period, fourth row or fourth period, fifth row or fifth period. So as we're adding more shells to the atoms, the size of the atom, or in I minus ion, the size increases. Okay? So if we just draw some just random, not to scale or anything, fluoride, chloride, bromide, iodide. So as the atomic size increases, the ion size will also increase. So I have minus chloride, bromide, iodide. So you see the size is increasing. The size of the ion is increasing. But the size of the ion is increasing, yes. And more importantly, the negative charges, you have only one negative charge on all these atoms or ions. So with a single extra electron, the size, since the size is large, that negative charge, the extra electron is able to spread out on a larger surface. So if it is spread out, it's more stable. So like, see, it's something like resonance. When we talked about resonance, we said, hey, I'll just draw that example again here. So you see that negative charge there comes in and then this goes there. So the negative charge is spread out over the molecule. Here the negative charge is spread out on a larger surface, making iodide actually the most stable. Okay? So iodide is most stable in this case. So you want to put that in the familiar ordering. Fluoride is less stable than chloride, which is less stable than bromide, which is less stable than iodide. Okay? So that's due to the increasing size of these ions. Iodide is the largest ion, the negative charge is spread out on a larger surface. So with that, let's just move elsewhere, another column here. Let's take a look at the elements in this column. So we're looking at oxygen and sulfur. So let's consider those ions, hydroxide and this one. Okay. So between these two, which one is more stable? So we look at this. This is oxygen is in the second row, sulfur is in the third row. So sulfur has a larger size. So this one is more stable between these two ions. So that's it. So this is a quite simple concept. But so this happens quite a bit in organic chemistry. We start saying stuff, we build stuff, right, to something. You start with some concept. We started with electronegativity. We explained how electronegativity helps stabilize certain types of anions. And then later on, like today, we said, oh no, that's there, but there's something else. So we need to be nimble and move and look at the most appropriate thing. Now, you may ask, hey, is there any experimental evidence for this? There is. Many times there is experimental evidence, and we'll come to that in later topics and later capsules. So we stop here to finish this.